Over two-thirds of this planet is covered in water. Of this vast amount, only 1% is accessible freshwater that can be found in rivers, lakes, and streams. In 2023, Google alone has used 6.4 billion gallons of water in their data centers. And as the demand for AI explodes, so does their insatiable thirst for water. But what are they doing with it? And can we even stop it? The most popular method of cooling data centers from the 1970s to the early 2000s was air cooling. So many data centers today still have this infrastructure. Air cooling involves using CRAC and CRAH units to blow cool air through server racks and maintain stable operation temperatures. With the advancement of technology, the density of transistors has increased exponentially, allowing us to fit more computing power into a smaller space, which comes with the additional thermal density requiring more advanced cooling methods. Evaporative cooling, like air cooling, uses air to cool down server racks. However, it is much more energy efficient. Ambient air is passed through wet pads, and the vaporization of water in these pads consumes heat, cooling down the air passing through. This consumes less electricity than CRAC units for the same amount of cooling. Adapting pre-existing data centers to use evaporative cooling is still much cheaper than most alternative cooling methods, hence its popularity. How effective is air for cooling? Almost all electrical energy that passes through a server rack is converted to thermal energy. This gives us the amount of heat that must be removed from a system to maintain constant temperature in a server rack. Using the first law of thermodynamics, we can describe what is happening in a server rack using the following equation. We can simplify the equation by assuming that the system is in steady state. A negligible amount of heat entering the system, changes in kinetic potential energy are negligible, and no work is produced. Since the only input of energy is electricity, we can rearrange the equation as follows, where the wattage of electrical power used in a server rack determines the mass flow rate of a fluid given the specific heat and temperature rise of the fluid. At atmospheric pressure and temperatures under 300 Kelvin, we can estimate the specific heat of air to be 1.005 kilojoules per kilogram Kelvin. The power density in a server rack for AI is approaching 50 kilowatts and expected to rise in coming years. If air is expected to reach a 10 degrees Celsius temperature rise, then we can determine the mass flow rate of air needs to be 5 kilojoules. The mass flow rate of air needs to be a massive 5 kilograms per second. This is why air cooling becomes obsolete in data centers, and why companies leading in AI are leaning away from evaporative cooling. Fortunately, there are cooling methods that can keep up with the thermal demands of AI that don't require water. In direct-to-chip cooling, a glycol-water mixture is passed through cold plates directly mounted to the CPU or GPU. This method, due to the higher specific heat of the water-glycol mixture, can handle servers with much higher power requirements. Under the same conditions of the evaporative cooler, you would only need a mass flow rate of 1.75 kilograms per second to provide the same cooling. In immersion cooling, servers are submerged in dielectric fluid to quickly dissipate heat. The coolant is then circulated in a heat exchanger to be reused. On the lower end, you'd still only need a mass flow rate of 2.63 kilograms per second to keep up with current AI demands. However, both methods are mechanically complex and have high maintenance costs. This means it's difficult to retrofit old data centers with the new cooling methods, and it's far more efficient to install in brand new data centers. Evaporative cooling may be a cheap, effective way to cool down server racks and data centers for now. However, the volume of water consumed is unsustainable and can't keep up with the growing power densities of AI. Eventually, data centers will need to bite the bullet and install more complex cooling systems if they want to keep up with the growing demand for AI.